Okay, hi everyone. Um, Thanks for coming to my talk. My name is Pedro. You can follow me on Twitter or GitHub under this handle. I work for YLD, where I'm a partner and chief futurist there. I'm a Node.js developer, and you'll see that I'm also an offline first enthusiast. If you were doing Node.js back in the very early days, you may know me from NodeTouch's screencast show, or from some Node.js related books, like the Node Patterns books. Today I'm here to talk to you about how to build a reliable checkout experience using Node.js, PouchDB, and replicated transaction documents. So here today I'm going to talk to you about e-commerce and the much dreaded checkout experience. The checkout is a journey that begins with the optimistic checkout button, but only really starts after the user presses the confirmation submit button. And behind the scenes, there's a bunch of machinery, old machinery that starts cranking once the user does that. And eventually, it ends in a success message and a confirmation email. But I'm more interested in what can go wrong, what patterns of failures can we extract from stuff that can go wrong. So there's a bunch of failure modes. The one that I'm most afraid of is this one, which is duplicate transactions. I've had this happen to me twice, and it kind of translates into the do not press me more than once button pattern that you see a lot on user interfaces. The other one is the undefined state. So you may have a spinner that spins indefinitely. It doesn't recover from a lost connection, for instance, or client crashes. So you may have a mobile phone, for instance, and you run out of battery while you're doing a transaction. What happens to that transaction? What's the state of that transaction? How can you recover from that? How do you know the state of the current of the transaction you were performing? I also want to talk about mobile in the context of e-commerce transactions. These are some stats about a first world mobile network. And these numbers here explain the amount of time that you can expect to be, the average amount of time that you can expect to be offline, effectively offline. And by being effectively offline, I mean you don't have connection to the internet. So this may happen if you have a 4G connection. You may expect to be around 1.3% of your time offline. But if you have a 4G connection, you can expect to be 4.1% of your time offline. And this is kind of a big number for me. And if you have a very modern 4G device, even if you have a very modern device, you'll be effectively balancing between 3 and 4G. You cannot expect to always be in 4G, where you can expect a lower offline experience. For several reasons. For instance, your mobile device may be running out of battery, and the device downgrades you to a lower bandwidth to save the battery, or the network kicks you from 4G to 3G because of congestion, or there is no backbone connectivity, and there is a lot of reasons why you will experience this more than this. And this is only for a first world modern mobile network. You can only imagine what it's like in developing countries, where the quality, not only because of the quality of the mobile network, but also because of the backbone connectivity, and more than that, the average quality of the devices, right? Because they will not implement the fastest protocols right away, and they will have weaker batteries, smaller antennas and weaker batteries, and you can expect to be offline much more than this. This last slide is stolen from Ilya Grigoryk's Google I/O talk. Ilya Grigoryk is a Google engineer that focuses on mobile networks, in the context of browsers. But it's a bit more than that. So I advise you to watch his talk if you want to learn more about gotchas of programming for mobile networks and how you can try to work around them. And he has also a very interesting book on that subject. It's a free book if you want to. But the main takeaway here is that to develop a reliable mobile app that uses a mobile network is particularly difficult. So being offline is not an exception, it's a given, and programmers should be aware of that. So what's the solution? Offline first is a movement that was created a few years ago, which main focus is to make web applications or applications in general work well while offline. So the community has created a set of patterns and tools and conventions to solve the offline problem. One of those is service workers. I'm not going to be talking about service workers today because it's the subject of another talk, and I'm not an expert on service workers. But there was earlier a talk about that, which I think you can also watch online. Also, you can watch this talk from Jake Archibald, also Google's engineer. He talks about instant loading, building offline first applications. If you want to know more about offline first in the context of building progressive web apps. I'm more interested in the side of data and transactions and how you deal with networking failures. So now let's try and grade how, I want to do an exercise, which is to grade how our applications deal with networking failures. So first is, the worst case is an application that doesn't do any error handling. So even if an error occurs, like a request fails, the application tells you that everything is okay. So the next one is an application where the customer is notified of the error if the error happens, but the customer can't do anything to recover from that. So he probably has to phone the customer service, say, I had an error, what's up? C, the customer can recover from that error, and this can be a refresh on the browser, and the browser application, the application is able to regain the state of the transaction, resume the transaction somehow. And B, the app can recover automatically from some of those system errors. And A, the app can recover from system and some user errors. And by user errors, I mean stuff like closing the browser or the device shutting down. The canonical example for this is the Uber application. So if you shut down the Uber application and while in middle of a transaction, you can open it again and it regains the state of the last transaction. But this last stage is particularly difficult and expensive to implement. Uber has put a lot of effort and time into developing all the necessary engineering around recovering from failures, from those failures. And why is that? Why is it so difficult? So let's take a look at a typical systems architecture for a typical e-commerce application. So these are a bunch of backend services. This is perhaps a third-party payment system. This is perhaps the accounting system. This is perhaps the identity management system. And this is an email service, for instance. In the context of a transaction, these services are all eventually going to be participating in the transaction. And typically, you want to create an application, a web application, or a mobile application. So you have to expose these systems through an HTTP API, which can be specific to the application or a generic HTTP API. And on top of that, the application, through the internet, performs the transaction hitting the HTTP API. What happens when there is no connectivity, when the device cannot contact the HTTP API? What happens if while you're performing a transaction, there is no connectivity here. How does the application react to timeouts, to gateway errors, to 500 errors? Is it able to recover from that? It probably is, but it's going to cost a lot developing for all the corner cases and to test all the corner cases. In my opinion, this is too much responsibility on the app developer to handle. And my thesis is that HTTP is the wrong level of abstraction for these types of transactions. This coupled with works on my laptop mentality usually leads to poor results. But there has to be a better way, right? So if you think of it, all you need is to synchronize the state between the client and the backend, the transaction state between the client and the backend. So in theory, if we have like a sync layer on the client and a sync layer on the backend, they all can talk to each other. And if this fails here and then comes back again, the sync layer is able to recover from that automatically without the application having to be concerned about recovering from those states. So we have to pick a sync protocol for this part, right? As Jan Lenhart said, friends don't let friends implement their own sync protocol, which I think is fairly intelligent. So right now we're going to use, for this example at least, we're going to use CouchDB and any of the variants of CouchDB that are compatible with the CouchDB replication protocol, sync protocol. So CouchDB is an open source database server that is, if you don't know about CouchDB, it's Docker oriented, so you can create an arbitrary documents, JSON documents, and store those documents inside that database. It has multi-version concurrency control, which is a way to manage the concurrency. So it has a sequential version identifier, and all the clients, if two clients write in concurrency, one of them will win and the other one won't, and the one that doesn't has to retry. It also has an interesting property, which is a changes feed, which is crucial for the synchronization protocol, which is CouchDB keeps all the versions, if you tell it to, it keeps all the versions of all the documents stored. So you can ask for the changes that the database has suffered since a point in time. And based on this, it implements a specific replication protocol, which these products implement with the honorable exception of Couchbase, which is not exactly the same protocol, but you can use a gateway to communicate with CouchDB. So, yeah, you can use all these products. Basically, we have this sync layer is going to be replaced by PouchDB on the client. So PouchDB is like the JavaScript cousin of CouchDB. So it runs on the browser, runs on the Node.js on the server, on the backend. And it synchronizes with PouchDB or CouchDB on the backend. And this database doesn't talk directly to the API. There's a CLERK process, which is built on Node.js, that listens to the changes the transactions are going to suffer here and communicates with the backend API on behalf of the application. Okay? So if you want to zoom into, for the case where there are many client applications, each one of them has their own client database, which replicates into the server-side database. So each client, each customer has its own database, which may seem a bit odd for people that are more used to MongoDB or traditional SQL stores, but it's a very normal pattern in in CouchDB. So each user has a specific database, and no user can access other users' databases. So it's a way to scale, horizontally scale, and to secure access rights. And also each database has a CLERK, which can be a process or can be just an object that listens to the changes on the database. So I told you one database per customer and one document per transaction. So the transaction will contain all the attributes that are necessary to complete the transaction. For instance, if I'm booking a plane trip, it will contain all the actual flights, contain all the people, the billing data, the payment token, whatever is necessary to complete the transaction. And this document will be not only updated by the client, will also be updated by the CLERK. So synchronizing both versions of the document, there is a sync protocol that replicates them bidirectionally, which gives offline tolerance to the application. So this protocol recovers from being offline automatically. So the application doesn't have to worry about being offline, other than just inform the user that, oh, yo, by the way, you're offline. That's why it's taking a bit longer than expected. So the CLERK reacts to transaction state changes. Each transaction has, you can define a finite state machine, and the transitions here are performed either on the CLERK or on the client. For instance, this is a very narrowed down example of a taxi-like application, like a Uber-like application. So we can go from taxi has been requested to driver assigned, driver en route, driver arrived, etc., or can be cancelled, and can be cancelled from any other point, I guess. I'm not sure. So the thing is that state transitions are performed in lockstep, either by the client or the CLERK. So yeah, the CLERK injects transaction changes when backend events occur. So the CLERK has the opportunity to listen to backend events. For instance, listen on a queue, on a message queue for events, and perform changes on the state of the transaction. For instance, you can listen to events like, has the ride been cancelled? And if so, you can update the transaction document with that state, and then the client application will get that new state and render the transaction appropriately. So let's look into some code. First on UI part. Here I'm going to use a library called Pouch Redux middleware. This library synchronizes the browser state, Redux state, with a PouchDB client-side database bidirectionally. So, which means that any change happening to the Redux state is replicated into the PouchDB database, and vice versa. So any change coming from the server on the PouchDB database is replicated into the Redux state. So this allows you to create a React Redux application very easily on top of this type of architecture. This is an example of Redux reducer. Basically, it's doing very simple things like adding a transaction, inserting a transaction, deleting a transaction, and editing transaction. This is the part that pertains, the only part that belongs to a specific transaction, which is just changing some properties on the transaction document. And that's it. That's all the client side has to worry about when on the actions that affect a given transaction. Let's look at the backend code. So I'm going to use a library called PouchClerk, and PouchClerk is a Node.js package that allows you to listen to changes, do exactly what I described, which is listen to changes on a given document and react to those changes, and also do asynchronous updates. I'm going to show you. So two things, state transitions and async updates. State transitions are just a function, a callback function that gets invoked once there is a transition. In this case, it's the arrived destination state that's been arrived. And here I'm calling the backend. I'm faking the call. There's a fake backend, and I'm calling arrived destination. But I could be calling anything else that Node.js allows me to. So I'm just going to implement this state transition and call the API, the backend API, for the client. Async updaters are reverse. So async updaters are more complex. I'm sorry about the aspect ratio. This is kind of a class thingy that has at least a start method, and you can take the opportunity to, on a start method, to listen, for instance, to subscribe to a message queue on a certain topic. On this case, we're subscribing to a cancel event on the backend message queue, and once that event happens, this function is called, and we're going to take the opportunity to change the transaction document. And once the transaction is done, is completed, the stop method is going to be called, and I'm going to take this opportunity to unsubscribe from the messaging service. This allows you to very easily model stuff that happens that will affect the transaction, but asynchronously. So it's time for a quick demo that uses all these, quick demo. So I recorded, I cheated, I recorded a demo because I didn't know if I was going to have Wi-Fi. Here I'm starting a static server, and here I'm starting a sync server. And basically I created this very simple application that's called drag and drop. It's Uber for dragons. So I'm going to request a dragon, and I'm going to select the pickup point here, destination point there, and you can see my awesome front-end skills here. I'm going to confirm the payment method. A bunch of dragons are flying around me. One of them is going to get picked as my driver, and my driver is. So this one got picked up. It's en route. He's going to pick me up, and it's going to eventually fly me there. And by the way, all this is open source. I'll share you the link after. So I'm going to rate the dragon, and my trip is finished. Now I'm going to show you the document, the transaction document, here on the lower pane. So you can see that the state of the document is going to change as I progress the transactions. Here is the state. Select payment method. I confirm, now it's searching driver. And all the attributes, the random attributes that are here are the ones that are necessary to render or perform the transaction on the back end. So here I have the passenger position, and the driver is en route. So the driver, whose name is Harold, location is changing, and the speed is also changing. Eventually, we are en route, so the passenger position is being updated, as you can see, in real time. In real time. Yeah, the trip is finished. Notice that when I rate, there is the rating here reflects on the document, and there is the revision. So this document has suffered 34 revisions, so 34 different states. Now I'm going to simulate network disconnections. So I'm going to request a dragon anyway. I'm disconnected here from the sync service. It's trying to reconnect, but I'm going to start a transaction anyway. And now I'm going to restart the sync server. Eventually it will reconnect. And now I'm progressing. I'm going to select the payment method, but before I select the payment method, I'm going to disconnect again from the network. I'm going to confirm the payment method. It's on searching driver. Now I'm going to start the server, the sync server again, and now I'm going to progress my transaction, and so on and so on. So you can see that it's recovering. I think I have one more disconnection, I think, after the driver is assigned. So here I'm going to disconnect. I mean, it's a bit like Uber, the Uber app, but with much less effort in recovering from these problems. Okay, so that one's done. Cool. Where is the mouse? Okay. Okay, so this is open source. If you're interested, you can check it out on GitHub, pgt/pouch CLERK example lab, and the slides will be online, so you can. I will tweet the link to the slides later. So where can we head from here? So I think this type of architecture supports, as you saw, long-running transactions. So not only performing e-commerce transactions like booking something, but performing these types of transactions where it spawns not only for seconds, but minutes or hours or days even. And extending that, you can use it for collaborative games. Like you can have two people working on the same transaction state, which is the whole game actually, and other other stuff that I couldn't imagine, but you probably will. So the slides will be available here. I will tweet the link, and that's all I have for you now. Thank you. I don't know if you have any question.
Hello, I couldn't help but compare this approach to the Meteor one, namely the
what? Sorry,
the Meteor approach, which has a core concept. One of the core concepts is database everywhere, which basically has a mini Mongo on the client and a Mongo database on the server, and it basically tails the log of the database to do the syncing. And I'm wondering what are the differences between this approach and the Meteor one.
Okay.
If there are any.
Okay. The question was this architecture is kind of similar to Meteor and what Meteor does with the MongoDB back database, tails the op log, and then syncs all the state into the client, right? So the main difference here is that CouchDB, I'm going to go into a rant here. CouchDB was created with sync in mind, and MongoDB wasn't. So Meteor is parsing the op log and doing strange stuff to be able to get that to assess the state of the changes, basically, to assess what changes were performed on the database. And CouchDB has that for free because it was built thinking about that from the ground up. And also, I don't know, I'm not sure, I'm not a Meteor and MongoDB expert. I don't know if you can use different databases, but CouchDB in this architecture, you use a different database for each customer. So there is no chance a customer can get another customer's data unless if he gets the same credentials. The chance is minimized here. And also the scaling aspect, the horizontal scaling aspect of having independent databases that you can spawn over multiple machines if you want to, and each customer gets assigned to one of those machines. Is I think it's an advantage. Also, Meteor is, I think Meteor has a bunch of plugins on the client, but by default, it uses the state is all in memory, right? Again, I'm not a Meteor expert, but here the state is all in storage, on the client and on the server. Well, you can use that. You can put that on memory if you want to. You can specify that PouchDB only uses memory storage, at least on the back end or in the front end, because this is not permanent storage here, right? You don't need this. It's a transient storage. You don't need to persist. This is not something that you'll need later, because the source of truth will be those back-end services. I hope I answered your question. Yeah. Okay.
I haven't actually heard of PouchDB before. Like I heard the name, but I didn't knew what it was. So I'm kind of like thinking, it creates like an instance of a database with the information of a given user, right? So if you have like shared data, imagine I'm a customer seeing a product, and he's a guy who's selling the product, and he edits like the price. Is it possible then I can see the price in real time? Do you see?
Yes, it is. It is possible. So in this architecture, you'd have to use async updaters. So you have to subscribe to product changes in that case. Sorry, the question was, so PouchDB, is it possible to do something collaborative, like there is some change on the product database, and then the customer sees the product change in real time, right? Was that? Oh, okay. Okay. Okay, PouchDB in this case can be on two places, on the client or on the server, okay, on the backend, and they both sync. The backend can be CouchDB or can be PouchDB or whatever other compatible database you want, right? But the client side is PouchDB, and so on the server side you create a database per customer. Right? So if there is a transaction coming in, a new transaction, and you can create a database for that transaction if you want to, or if the user logs in, you can create a database for that user if you want to. So you can track all the history of the transactions if you want to, but it will be a different database per client or per customer, whatever the application wants to.
Then another guy is connected to another one. Like the clerk has to subscribe to changes.
Exactly. So this is not something that you want to. This is not a persistent store. This is not something that you want to use for changing central records. The central source of truth will be the backend system. Okay. So you have to do something convoluted, which is if you want to, the user is checking. Well, you usually don't want to do that. If the guy is checking out a product and he has a certain price, you don't want to change the price after he confirms it, right? But if you wanted to, it's possible doing async updates. So the backend system, when there's a change in price, publishes a message, and the clerks that are interested in that product will listen to that message, will receive that message, and will perform a change wherever it's necessary, because they are subscribing. So each different client that's interested in that product or is checking out that product will have the clerk subscribe to that topic and update the transaction state accordingly with a change in price. If the change in price is cheaper, it's a nice surprise. But if it's not, if it's more expensive, that's hard. But the main thing is that the central source of truth is the backend systems. It's not the layer, the sync layer. The sync layer is just something to help on sync. That's it. All this and below here is the source of truth. This is where you make changes to products. Okay? It's not here. The clerk is acting on behalf of the customer and calling the API on behalf of the customer. That's it. Okay? Okay? Any more questions? No? Okay. Thank you.